the last lesson for this unit. It's called the work energy theorem, Chris. And you may recall way back when I defined energy, I said that energy was the ability to do work. Let's write that in. And I gave you two definitions for work. The first definition that we're going to write on the left, I said that work was equal to, I gave you an equation. Force times distance, as long as the force and the distance are in the same direction. Or I also said that work equals the area under a force versus distance graph. That was our second definition of work. And Jordan, specifically, we used that if our force was changing. That first one, work equals force times distance, has two restrictions. The force and the distance have to be in the same direction. That one you guys almost always remember. But another one, which I didn't do a big song and dance about, is the force has to be constant. If it's changing, that equation won't work.
Are you going to have the graph? Are you going to have one with us?
Am I going to give you one like with a graph?
No, with a curve.
Not a curve, but a straight line, sure. Like a slanty line? Yes. Curve? No. Curve, that's why Sir Isaac Newton invented the calculus. He wanted to try and figure out two things. How to find the slope of a curve, because rise over run doesn't work. But the slope, you guys have learned in Science 10 and Physics 11, does mean something. And he wanted to find the area under a curve, because if it's a curve, you can't just go length times width, because the length and the width are changing as you move along. There's a third definition for work. And in fact, it's called the work energy theorem, which, if you're clever, may suggest to you that it'll have work and energy in the same equation. And it will. The third definition for work, the work energy theorem, says that the amount of work that you do on an object is equal to its change in potential plus its change in kinetic. Where change in anything is equal to what? Ooh, boy. Put your pencils down. I am going to ask you all a question. I am going to say, what's change in anything equal to? And all of you are going to say back in a loud, authoritative voice, final minus initial. Worth memorizing. What's change in anything? Final minus initial. Chris joined the party a bit late, so we're going to do it again. What's change in anything? Final minus initial. Kelly didn't move her lips at all, so we're going to do it again. What's change in anything? Final minus initial. You really think in the front row you were going to get away with that twice in a row? Come on. I have my eyes everywhere. What's change in anything, Jamie?
Final minus.
So if I wanted to rewrite this equation, really, it would look like this. Example 1. A cyclist weighs 65 kilograms. His bike weighs 7.2 kilograms. You know what? Before we go further, then, what's the total mass we're talking about? 65 and 7.2. Let's just write that down. 72.2 kilograms. How much work, Nick? How much what? How much work, Nick? How much what? Work does it take for him to increase his speed from rest to 5 meters per second? Now, work is force times distance. Look at this question, Nick. Do you see a force or a distance anywhere?
No.
So that's not going to get us. That's not going to work. Haha, no pun intended. It's also the area under a force versus distance graph. Abe, do you see a picture of a graph anywhere in this question? Okay, I'm not going to use that. By the way, the work energy theorem, I'm sneaking in some physics 12 with you guys right now. Our third definition of work is, and this is my process, it's always, well, can force times distance work? No. Is there a graph? No. Well then, obviously, I'm on my third definition of work. Change in potential plus change in kinetic. Now, we need to use our imaginations here a little bit. We're riding a bike. Does this question imply like a hill or anything like that anywhere in it? Let's assume we're on a flat surface, which means what's our change in height?
0.
So what's our change in potential energy?
0.
Because our final and initial would be the same. I think we can say Ha-ha! That leaves us, Jordan, with change in kinetic. Kelly, what's change in anything? Thank you, Kelly. What a deep voice you have. Oh, let's stay the same color, Mr. Duke. Yeah. All right. Work equals, hey, what is the equation for kinetic energy? Brad, what is the equation for kinetic energy? You know it, so final would be a half mv final squared, initial would be a half mv, yeah, initial squared. So a half mv final squared minus a half mv initial squared. Do the m's cancel? Careful. Abe is correct. Abe says no. Why not? Well, there is an m in the last term. There is an m in the second term. Is there an m in the work? No, so don't be going cancel happy here. That's why I had to give you the mass. But now I think it's plug and chug. Let's see. It's going to be 0.5. Oh, you know what else I noticed, by the way? I can cross out one of these completely. What's my initial velocity? It says from rest, yes? So I could do that, I guess. I didn't notice that until just now. I wasn't looking at my numbers carefully. It's going to be 0.5 times 72.2 times 5 squared. What do you get? 903? Anybody else? Okay. 903 even? 902.5. 902.5 even? Yeah, okay, let's go with that for now. So to go from 0 to 5 meters per second, we had to add 902.5 joules of kinetic energy. Hey, where'd that energy come from?
His food, his muscles.
Yeah, the biker. Yeah. And where'd he get it from? Food, chemical energy stored as food. Okay. What did he increase his speed by? By how many meters per second? 5. Take a look at B. What's he increasing his speed by? By how many meters per second? I wonder if the answer will be the same. Let's find out. Because it wants to know how much work to increase your speed from 5 to 10. Well, work is force times distance. Cliff, do you see a force or a distance mentioned anywhere in this question? Work is also the area under a force versus distance graph. Janaya, do you see a force versus distance graph anywhere in this question? You know what? Then our third definition of work, and by the way, when you get to Physics 12, that's your checklist. Try force times distance first, then try a graph. The graph one's usually pretty obvious, Joel. Often you'll just skip it instinctively because you'll know, no graph! This is the one we actually end up using a lot more in physics because in the second half of the course, the forces aren't constant. This one still works. Oh, you know what, Nick? I think, again, we can argue we're staying on the ground and ending up on the ground, so no change in potential. In fact, I think, again, we can actually say it's going to be, hey, what's changed in anything, Kelly? Darn right it is. That's music to my ears. So I'm going to get this. Work equals a half mv final squared minus a half mv initial squared. Well, I should get the same answer, I think. I'm only going up by 5 meters per second, just like before. Let's see. It's going to be 0.5 times 72.2 times 10 squared minus 0.5 times 72.2 times 5 squared. See if you get the same answer. Or do you get 2,707.5? Maybe. I know a shortcut. I didn't actually do the math. I used the previous answer to figure out this one. Sorry, Cole, what'd you get?
What you said, 2,407.5 joules.
Oh, heck, let's go 2,708 joules, because that's 4 sig figs. That's ridiculously accurate. Wait a minute, Mr. Dewick. We increased by 5 meters per second, just like before, but it took more work? Yeah. How many of you have ridden on a bike before? Okay. This is why once you go from, I'll make some numbers up, from 0 to 10 meters per second, which is not too bad at all. You can cycle at 10 meters per second. To gain another 10 meters per second tires you out way more than gaining that first 10 meters per second. How come? Because, Nick, it takes way more work, way more energy. Where's the energy coming from? You, the cyclist.
But why?
Because mathematically of that there. The fact that this also has to do with Brad's earlier question about the squareds. The fact that it's a velocity squared and a velocity squared. If you want to, I'll do a lovely algebraic proof with you in a second with no actual numbers, and you can spot the pattern. Let's try C. A gain of 5 meter per second increase. How much energy to go from 10 to 15, I wonder? You know what? Let's jump straight to the equation. We know it's going to be a half m v final squared minus a half m v initial squared. It's going to be 0.5 times 70. Come on, pen. 72.2 times 15 squared minus 0.5 times 72.2 times 10 squared. You're going to get a bigger answer than B, even though it's still a 5 meter per second increase. I think you get something in the 4,000-ish.
4,500. 4,513 joules.
Okay. I don't know if you've ever asked yourself this question. Car engine, a source of energy, yes?
Yes.
So how come you can't hold the gas pedal down and just keep going faster and 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 faster? Why does every car eventually max out its speed? It's because the faster you go, the more energy it takes to go just a little bit faster. And eventually you reach the limit of what the engine can put out. That's the maximum kinetic energy it can put out. You've maxed out your speed. And every little bit extra takes way more energy than it took to get there. That's one consequence of the work energy theorem. That's why you don't work up a sweat cycling at slow speeds. You work up a sweat going from a slow speed to a fast speed and maintaining that fast speed. Next page over.
Then can we also make the argument then, if like you're doing chores or taking out the garbage and stopping your parents, why are you taking everything in one load? Can we say because it's actually easier than traveling back and forth then? I'm not sure because you wouldn't be going, you'd be going slow.
Hang on 1 second. Model rockets. Physics 12, I almost always start the year, lesson 3 or 4, we launch a rocket. I can do it in grade 12 because September, I know I can guarantee at least one nice day. By the way, I have a neat outdoor lab that I've been trying to do for about 2 weeks that I don't think is going to happen. We calculate your own horsepower. Yep.
How do you calculate your own horsepower?
If I get the lab, if we have a sunny day before spring break, we'll do it. It just hasn't been cooperating. So anyhow, launching a rocket. A rocket starts out on the launch platform and it gains both potential and kinetic energy. Where does that energy come from? The rocket engine, the fuel inside the little rocket. For a Model 1, it's not really fuel. It's like a little powdery thingy. Okay. Well, read with me. A 0.15 kilogram model rocket reaches a height of 340 meters when launched. If the top speed of the rocket is 85 meters per second, how much work does the rocket engine do on the rocket? What are they asking me to find here, Nick? How much what? Work. Work is force times distance. Now, I do see a distance there, 340 meters, and I could say that the force was mg gravity, but I'm also seeing a speed there. See it? A change in speed. I don't think I want to use the force times distance one, because I don't think that's all the work that's being done, Stefan. Oh, work is also the area underneath the graph. Stefan, you see a graph? No. You know what? Work is change in potential plus change in kinetic. And Kelly, what's change in anything? By the way, I'm not going to cross out the change in potential this time. I'm pretty sure there is a change in height. Not a flat road, yes? So it's going to be potential energy final minus potential energy initial plus kinetic energy final minus kinetic energy initial. I'll space them out just so I can see that those are the ones that go together. Are any of these 0? Is your final height of a rocket ship at the top 0? Is your initial height of a rocket ship when you launch 0? Yeah. Yoink. Now, got to be careful with the kinetic final. You could argue that at the very, very top, the rocket does come to a stop for a split second. What I really mean, though, is does the rocket ship gain kinetic energy? Yeah, because I think it started from rest. I think I want to cancel that out. And when it says the maximum speed of the rocket is 85, what we're saying is the engine had to supply that much kinetic energy, too. So I'm not going to cross out the final, even though you could argue, well, that final doesn't mean at the top. For the kinetic energy, what I should really have is kinetic energy maximum minus kinetic energy minimum. Is that okay, Greg? Nod your head. Sit up. Look awake. Be alert. Let's go. Work equals mgh final plus a half mv final squared. And really by v final, Sean, what I mean is v max. Did they give me the... Oh, I think I can plug and chug. Let's see. They gave me the mass, 0.15. They gave me G, 9.8. They gave me H, 340, plus 0.5 times 0.15 times 85 squared. If I want this rocket ship to hit a top speed of 85 meters per second and hit a top height of 340 meters, what's the minimum amount of energy this rocket engine better have contained within its chemicals? Oh, and this is ignoring air resistance. Although rockets are pretty aerodynamic, there's a reason why they all look the same. What do you get?
5,540 joules.
Anyone else? No? Yes? No? I'm sensing no. Okay, let me type it myself. 0.15. Even Nick is curious enough to start typing. I love it. Anybody here launch or have model rockets? I always have a couple of kids. You have? Oh. Oh, when typing? Thank you. I would have caught that, but I would have caught it after the error glitch, so thanks for letting me know. I would have said, that's way too big. 0.5 times. So you didn't raise your hand to say that you had model rockets. You raised your hand to say that I'd made a mistake? Oh, sorry, I was in love for a second. I thought a fellow nerd, but no. That's totally wrong, Mr. Duick. Oh, because it's plus, Mr. Duick, not minus. It's not a change in. Do you get 1,041?
Yeah.
As a
1,042.
Thank you, Sean. Did you hear him slap me upside the face after I rebuked Cole earlier? I said, did you get 1,041? And you heard him say, no, 1,042 actually. And why don't you say, learn to round off? Come on, say it.
Learn to round off.
I humbly say you are correct. Man, it's been a while since I've been smacked upside the head like that. Joules, because it's work. So, Nick, I would assume, so I have a couple of model rockets. On the side of it, it says, flies up to a height of blah, 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 blah. I would guess that with the biggest engine that it can take, if you calculate how much potential energy that engine contains in chemicals, and then you go mass of the rocket times 9.8, you can figure out what height it'll hit based on assuming all of the energy turns into potential. Again, you'll lose some to air resistance. Oh, you lose a lot to heat, because rocket engines, when they fire, even after they come down, they're too hot to hold for about 60 seconds, so you're giving off a fair chunk of heat. It's still pretty fun, pretty cool. If you're looking for a cheap, inexpensive hobby, you can get a kit for about 30 bucks, and then the engines themselves are about 5 bucks a piece. If you have little nieces or nephews and you want to be really, really popular, what kid doesn't like to count down from 10, press a button, and see something blast off? I'm the cool one. Motorcycle video. Might have. I don't know. Was it coming through the wall? Sorry, I need to turn it down a little bit then. Whoever this person is, they're psychotic. Don't do this at home. But there's some good physics here. No. I need to get one that clearly had a speedometer in it because I needed some data, some good data to use. So here's a guy on a motorcycle. Why are we looking at the sky right now? Please don't try this at home. The outside speedometer is miles per hour, and that's the one that we can read the clearest. So what's his speed in miles per hour? Can you see it? Okay, he's doing 220. He's moving pretty good. Does he have kinetic energy? Fair bit of kinetic energy, it turns out. Is he gaining or losing kinetic energy? Where is that energy going? Or, let me ask you this way. What is doing the work on the motorcycle to bring it to a stop? Because work is change in potential plus change in kinetic, and there's clearly a change in kinetic. Brakes. The brakes. If we're looking for a simple, the brakes. In the form of what? Lots of heat. Lots. I wonder, if we get his final speed, could we calculate how many joules of energy the brakes had to absorb? Oh, okay, take your pencils out. You need to record a little bit of data. So, V initial, can you write down 220 miles per hour? We'll do the conversion after, but let's at least get our data. And the other thing we want to do is we want to find out how long it takes him to slow down, because if we find out how long it takes him to slow down, not only can we figure out how much work, I think if we divide by the time, we can figure out how many 60-watt light bulbs he could burn by doing this.
How do we know that he's not just let off the throttle and it's just putting its little bit of brake?
I'm pretty sure you're not slowing down this fast. Okay, actually, Nick raised a good question. I'm listening in the change of the engine. I think it's the gearbox and the brakes that are bringing him to a stop, but I'm going to lump that all into, you know what, the bike instrumentation mechanical part is bringing him to a stop, and let's call it the brakes. Good point. Okay. If you look at the clock in the bottom left, you people in the front row, Janaya and Jordan, you can see, I think, can you write down time initial 50 seconds? This will be my high-tech way of timing this.
Very accurate.
That's going to be within a second, which is 1 sig fig, 2 sig figs maybe. Okay, he's slowing down, he's slowing down. See, I think this is braking because I don't hear the engine rev changing like as though he was gearing down. I think he's put the clutch on and he's braking. We'll stop right at 100. So V final, 100 miles per hour. And time final, 67 seconds. 1 minute 7. So we got our data. Except I need to write that down. So, what was V initial in miles per hour? Sorry? I didn't hear. 220? miles per hour. We need to get this to meters per second. I don't know how to do that, but I can get miles per hour to kilometers per hour. Does anybody know the conversion factor?
1.6.
Ooh, nice.
Isn't it 1.64?
We'll be, you know what? We're rough enough in my timing system. I think we'll go with 1.6. I think we can say this. Miles is on the top, so I want miles on the bottom. I want kilometers on the top. 1 mile is the same as 1.6 kilometers. Hey, we're doing some good old unit conversion from October. Now that would get us into kilometers per hour. See it? Kilometers per hour to meters per second. There I've told you there's a shortcut. Memorize it. What's the shortcut? It's something to do with the 3.6. Times or divide?
Divide by 3.6.
I'm not sure. Put your pencils down. Cole says, I'm not sure. I think it's divide. I don't. You know what, Cole? Here's what I always do. I go to the easiest speed for me to work with, the freeway speed, which is what? 100. And then I say, Cole, it's either times by 3.6 or it's divide by 3.6. Which one? Well, if it was times by 3.6, I can do that in my head. 100 times 3.6 in my head is what? Really? 3.6 times 100 in your head is what? That would mean, if I times, that I was traveling 360 meters every second, that I was passing 3.5 football fields every second, that I was passing 3 farms every second. I've been on the freeway, and I've looked out the window. I'm not passing 3.5 football fields every second. I'm not passing 3 farms every second. Timesing is wrong. By the way, I still do that to this day. I've gone on a rant with you guys. I don't memorize stuff that I can derive in 1 second of thinking. And this is something I can derive in 1 second of thinking. I've memorized the number 3.6. And then if you see me, my eyes will go glazed for a second. And I'm thinking, well, 100 times 3 point. That's way too big. You know what? To go from kilometers per hour to meters per second, we divide. To go the other way around, we multiply. But for now, divide by 3.6. Okay, can you crunch the numbers? 220 times 1.6 divided by 3.6. What is our V initial?
97.8 meters per second.
Is that really, really accurate, or are we doing rough measurements?
Rough.
Then you know what? Let's pick a nice number. Okay? About 100 meters per second. He is doing about a football field every second, which is, I mean, your reaction time, stuff. What was V final? 100 miles per hour, right? Okay, now we've worked through the conversion, so it's going to be times by 1.6, divide by 3.6. How many meters per second is V final? Should be a little less than half of 100.
45.
45? And the last thing, what was the delta T? What was the change in time?
15 seconds.
Sorry? 17 seconds. Okay. So the first question we want is, how much work to stop? Well, work equals force times distance. Do you see a force and or a distance anywhere in this question? No, no. Hey, work is also the area underneath the force versus distance graph, Roy. Do you see a graph here? Then here's our new definition, the work energy theorem. Work is going to be the change in potential plus the change in kinetic. By the way, you guys saw the road, yes? I'm pretty sure, Kevan, it's flat, yeah? I certainly didn't see hills in there. Oh, and Kelly, what's changing anything? You'll never not lip sync again. I know. So it's going to be a half mv final squared minus a half mv initial squared. Because, Brad, as you pointed out, kinetic energy is a half mv squared, yes? That's going to be 0.5. Oh, we need a mass. So I wrote at the top there, assume the mass is what? What I did is I Googled 3 or 4 top bikes. I looked at their masses, took an average, and added a passenger. I don't know what kind of a bike this is, but it's clearly a high-performance bike. It's not a little Yamaha 80 or something like that, right? Obviously. So I Googled a few of the big ones. I did this about 5 years ago. I don't even remember which ones I Googled. But anyways. Looks like a what? Okay. V final was 45 squared minus 0.5, 300, 100 squared. By the way, did the bike lose energy or gain energy? Should I get a negative or a positive answer? I think in terms of the work that was done on the bike, it's negative. Now, that energy had to go somewhere. We'll talk about that in a second. You're going to get a big number. You're going to get a big number if you bother typing this into your calculator and following along for the sheer love of learning. What do you get? Negative 1, comma.
196,250.
Or, since we've been really rough, how about negative 1,200,000 joules? About 1.2 million joules. Oh! Next thing I'd like to know, how many watts of power? What's the equation for power? Work over time. Do we know how much work? Yeah. Oh, did we get the time from the video? Oh, cool, 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 cool. I'm going to ditch the negative because what we're really saying is the motorcycle lost work, lost energy. The brakes gained energy, probably in a great deal of heat. So it's just going to be, I'll use Cole's number, 196,250 divided by, what was our delta T? 17. Oh, it's still on my screen. One 196,250 divided by 17. You get that? Ish?
Yeah.
I've rounded off. 70,400 watts. Or, just to put it in perspective, can you divide it by 60? Take that number, divide it by 60. How many 60-watt light bulbs could we have powered?
1,172.
Sorry, what? How many?
1,172.
Over 1,000? Actually, for 1 second, because a watt is that many joules per second of power, for 1 second.
What would the power of one per?
A fair chunk of time. Now, anybody here own or drive a Prius? Okay, one of the neat things about the Prius is they've recognized that that is wasted energy. When you brake a Prius, when you slow a Prius down, instead of bleeding off the energy into your brakes for heat, they bleed off that kinetic energy through a clever system back into the batteries. When you brake, instead of it going wasted as heat, because you can see there's a fair number of light bulbs there, why not charge your batteries with that? Which you do. When you stop, the batteries get recharged, which means with a Prius, unlike most other vehicles, you get better gas mileage in the city with the stop and go than you do on the freeway. You may have noticed now, especially in downtown Vancouver, almost every single taxi cab is a Prius. Why? Do taxis do a lot of stop and go driving? Smart stuff. I used to do momentum before I did work and energy, and this is a really cool question. It's called the ballistic pendulum. It combined momentum and energy. Our next unit is momentum. I flip-flop the units around, and I keep forgetting to take these notes off of this lesson. So all we're going to do is preview of coming attractions, and preview of coming attractions, and preview of coming attractions, and roller coaster, preview of coming attractions. We've done roller coasters, but we haven't done roller coasters that crash into each other. Crashes are what you analyze momentum with in the next unit. So that brings us to Mr. Dewick's Nerf dart gun. Let's analyze it. So the distance we pulled back, Jordan accurately measured. He said that was 0.05 meters. Force required, well, I had to pull with 5 kilograms. How do I change kilograms into newtons? Multiply by what? 9.8. Oh, yeah, we actually got an application for this. Multiply by 9.8. So how many newtons of force did I pull with?
47.5 newtons.
I think it's exactly 49 if you go 5 times 9.8, isn't it? So how much work did I do? Well, work equals force times distance. I'm going with that one because I have a force and I have a distance, do I not? 49 times 0.05. In theory, how many joules of energy did I store as potential energy in my little Nerf gun? 2.45? So that's how much potential energy I stored. This isn't gravitational potential energy. This would be, I don't know, air compression potential. Whatever, I don't know. It's potential. It's stored energy. I know that. I don't know if it's springs in there or air compression or what. I got to take it apart one of these days. Oh, what did I say we needed next? What's the next thing we need to fill in here? Read, next line. What is it? Oh, we need the mass of one Nerf dart gun. Conveniently, I got my little scale back there. Let's throw it on the scale. Reset. Oh, that was very good. Let's try that again. Reset. Stay. Oh, nice. 1.5 grams even. Nice number. Would it be any better if I made them up? Ooh, that was grams. 1.5 grams. We better change that to kilograms. So, M equals 1.5 grams, which is 0. How many zeros and then a 1.5?
0.0015.
2 zeros and then a 1.5 kilograms. When I pull the trigger, what happens to all of my potential energy that's stored? What does it turn into? Kinetic energy, which means I should be able to figure out the theoretical speed of my little gun here. In fact, I think I should be able to say this. All of the potential turns into kinetic. Yes? All of the potential, which Roy, we said was 2.45 based on our quick little measurements there, mass, force times distance, should turn into, hey Brad, what's the equation for kinetic energy? A half. I'm going to go a half mv squared. And Brad, folks, we want to get the v by itself. I can ignore the 1. What's the 2 doing? Dividing, yes? So how will I move the 2 over? Times. What's the m doing? Timesing. So how will I move the m over? So I think I'll get this. V squared equals 2 times 2.45 divided by, what's the mass? 0.0015. Not quite done. How'd I get rid of a squared? Okay. My theoretical speed should be the square root of 2 times 2.45 divided by 0.0015. That's what it should be. Is it? Let's find out. What'd you get?
57 meters per second.
How fast? 57? Wow.
I got 2309.
Oh, 23?
No, I think I
57?
1001 is that?
Did you forget the square root?
Yeah.
So square root.
I did.
No, I don't think you... By the way, to type this in, because you got to be able to handle this on your test, folks. Don't square root at the beginning. Go 2 times 2.45 divided by 0.0015. Answer, square root of that, which is 57. You've seen my Nerf dart gun. Do you think it's going 57 meters per second?
Oh, no.
Higher or lower, do you think? Let's find out. So the actual speed as measured with my radar gun, V was 50 kilometers per hour. How many meters per second? How do I go from kilometers per hour to meters per second? Okay, so what is that?
14.
Sorry? 14 meters per second? Roughly, I think it's 13 point something. But 14, we'll go with 14 because we're being very rough. How much energy did I lose to friction?
43.
Well, let's see.
Oh.
My kinetic energy theoretical was 2.45, right? Yes?
Yeah.
My kinetic energy actual was a half mv squared. It was 0.5. What was the mass? 0.0015. And the mass that we measured was 14 squared. What was the actual kinetic energy we got out the other end?
0.15.
So how much? You're right. How much?
0.15.
Wow. We put in 2.5 joules, basically. We got out 0.15 joules. Friction, and Greg, I'm calling it friction, but it's sound, friction, heat. Maybe if it's air compression, maybe there's a leak. I don't know, but how much did we lose? Well, we started with 2.45. We got out 0.15. You know what? I'm pretty sure we lost 2.3 joules of energy to friction, heat, all sound, all that stuff. Hey, how efficient is my Nerf gun? Not very. Yeah, let's quantify it. So we said that efficiency, remember the funky symbol for efficiency was that thing, is smaller number divided by bigger number, or in this case, how much energy we got out divided by how much energy we put in times 100 to make it a percent. How much work did I do? How much energy did we put in? Aaron, 2.45. How much energy did we get out? What was the actual kinetic energy of my bullet? 0.15 times 100. 6% efficient? There is a reason that armies have not moved to Nerf as their primary means of settling disputes. Oh, you know what? Let's rephrase it. There is a reason why you don't hear of too many Nerf deaths in the newspapers. I'm pretty sure I could fire this at point blank range, maybe even right into my eyeball, and I'd still be okay in the long run, although it would probably hurt like crazy. Nerf. Not too many lawsuits over Nerf. And there is a part of me that says, honestly, if it does injure you, maybe I don't want your gene pool, you know, part of our... Anyways, that's a whole other issue. What's your homework? The quiz. I got a couple of videos to show you.